The topic is magnetic boundary conditions. To determine the boundary conditions, we use two laws. First is Gauss's law for magnetic field and second is the Ampere circuit law. According to Gauss's law, closed surface integration B dot ds equals to 0. And according to Ampere circuit law, that is a closed line integration H dot dl equals to I enclosed. So here we use two magnetic fields. First is magnetic flux density B vector, that is around a closed surface, and second is magnetic field intensity H vector, that is around closed path. So here to determine the magnetic boundary conditions we use a Gauss's law and Ampere's circuit law. In Gauss's law we use a closed surface and in Ampere's law we use a closed path. So the first is we use a Gauss's law for magnetic field, that is closed surface integration B dot ds equals to 0. Here the magnetic field is a magnetic flux density B vector. The first step is we have to break the magnetic flux density B into two parts, that is having a normal component and tangential component. And here we consider a boundary between two magnetic medium. We call it medium 1 having permeability mu1 and medium 2 having permeability mu2. In medium 1 we consider a magnetic flux density B1 and in medium 2 we consider magnetic flux density B2. In medium 1, magnetic flux density B1 having two components, that is normal component and tangential component, that is denoted by B1n and B1t, and n denotes the normal component and t denotes the tangential component. Similarly, in medium 2 we consider a magnetic flux density B2 and its normal component is B2n vector and tangential component is B2t vector. Now to determine a boundary conditions, we apply a Gauss's law, that is a closed surface integration B dot ds. For this we take a closed surface. So here we take a Gaussian surface, that is an assumed surface. Half of the surface is in medium 1 and half of the surface is medium 2. And here the closed surface having a cylindrical symmetry. This cylindrical Gaussian surface having a height delta h and having a cross-sectional area delta s. Half of the delta h is in medium 1 and half of the delta h is in medium 2. Now taking a closed surface integration, the closed surface integration can be divided into three integration, that is integration for top surface, integration for the bottom surface and the integration for the curved surface. Now we apply the integration of B dot ds for the three surfaces and equate it to 0. So the first surface, that is the top surface. Here the top surface having a component of B1, that is normal component B1n, and this surface having a direction that is towards B1n. So the dot product of top surface is B1n into delta s. Bottom surface, here the direction of this bottom surface is towards negative direction of B2n. So the second integration is minus B2n into delta s, because this having a normal direction that is opposite to B2n, normal component of B2. And the third integration, that is the surface integration of the curve. The third integration is 0, because as we take a differential surface on the surface, curved surface, we find that it has its equal and opposite differential surface which having a negative value. For example, here the right side differential surface having a direction towards positive tangential vector of B and its left side differential surface having a direction towards minus tangential vector of B. So the net is 0. So the third term, the surface integration B dot ds equals to 0. So we get only the two integration, that is for top and for the bottom. After equating, we get B1n equals to B2n. This shows that the normal component of magnetic flux density B is continuous at the boundary. Now we can write B equals to mu h. So the equation becomes mu1 h1n equals to mu2 h2n. And from here we can write h1n upon h2n equals to mu2 upon mu1. So this condition shows that the normal component of h vector is discontinuous at the boundary. Means it depends upon the value of mu2 and mu1. Here the magnetic field intensity H undergoes some change at the interface of the two magnetic medium. So by using the Gauss's law, we get two conditions. One is the continuous condition, that is normal component of B is continuous at the boundary, and the second is discontinuous condition of magnetic field intensity H. Now we consider a second law, that is the Ampere circuitry law, that is closed line integration S dot dl equals to I enclosed. From here we again consider a boundary between two magnetic media. Media 1 having permeability mu1 and media 2 having permeability mu2. In media 1, we consider a magnetic field intensity H1 and it has a normal component H1n and tangential component H1t. Similarly, in media 2, we consider a magnetic field intensity H2 having a normal component H2n and tangential component H2t. Now, for the Ampere circuitry law, we use a closed path. So here we consider a assumed closed path. Half of the closed path is in medium 1 and half of the path in medium 2. So here a rectangular closed path is considered here, having a dimension that is delta h and delta w. Delta h is the height and delta w is the width. Half of the delta h is in medium 1 and half of the delta h is in medium 2. Here we also consider that there is a current flowing on the surface of the boundary, and here we consider that the current is flowing into the page and denoted by cross. Since the current is flowing inside the page, so we use the right hand thumb rule. The thumb is denote the direction of the current and curl of the finger denote the direction of the closed path. So here A, B, C and D is the closed path and we move clockwise. Now apply a closed line integration S dot dl equals to I enclosed. Since there is a surface current flowing on the interface of the two magnetic media, so we consider a surface current density, and the formula of surface current density is equals to current upon perpendicular distance. So here, since the current is flowing inside the page and the perpendicular distance is delta W. So the perpendicular distance is delta W, so we can write current in the terms of surface current density, that is K into delta W. So the right side of that is current is equals to K into delta W. On the left side we take a closed line integration. The closed line integration is break into four paths, that is from A to B plus B to C plus C to D plus D to A. So as we move from A to B, that is in medium 1, and this path A to B is in the direction of H1t, and the dot product of S dot dl is equals to H1t to delta W, because in this path the direction is from A to B. From A to B the direction of dl is same as that of H1t. So the direction is same, so the dot product is 1 and we get a magnitude that is H1t into delta W. Now as we move from B to C having a half path in region 1 and half path in region 2. So half path of BC in region 1 and its dot product, that is S dot dl, here as we move from B to C, that is opposite to H1n, and its dl is delta H by 2. So we get minus H1n delta H by 2. And the half path from B to C in region 2, here this is also opposite to the H2n vector. So we can write minus H2n into delta H by 2. Now as we move from C to D, we find that it is opposite to H2t vector. So we can write minus H2t into delta W. Delta W is the distance magnitude of DL vector. Plus, now we move from D to A. Again, D to A is break into two half path, delta H by 2 in the medium 2 and then half path in medium 1. In medium 2, the half path having a direction same as H2n. So we get plus H2n delta H by 2, and in half path in medium 1 is again in the same direction of H1n. So we get H1n delta H by 2. So in this way we can write a closed line integration by break it into 4 paths and determine the H dot dl accordingly. So after cancelling the terms, we get bracket H1t minus H2t delta W is equals to K into delta W. From the left and right side, delta W is cancelled and we get H1t minus H2t equals to K. So this is a magnitude term. So from here we find that the tangential component of H vector is also discontinuous. That depends upon the surface current density K. This is a magnitude term. We can write in a vector form as within bracket H1t vector minus H2t vector cross normal unit vector 1 2, that is equals to K vector. Here we take a normal unit vector from region 1 to 2. So here we take a care that within bracket we have H1t minus H2t. So we take a unit normal vector from region 1 to 2, and that is equals to surface current density K vector. Now we consider a case when the boundary is free of current, means when there is no surface current density. In this case, H1t minus H2t equals to 0. So we observe that the tangential component of H vector is continuous at the boundary when there is no current. When there is no surface current density at the boundary, we get a continuous boundary condition of magnetic field intensity H. That is, the tangential component of H vector is continuous at the boundary. And we know that B equals to mu H. So we can write in terms of B and mu. So H1t equals to B1t upon mu1 and H2t equals to B2t upon mu2. From here, we get a condition that is B1t upon mu1 equals to B2t upon mu2. So here we observe that the tangential component of magnetic flux density B vector is discontinuous at the boundary when there is no surface current density at the boundary, when the boundary is free of current. So these are the boundary conditions. In the first case we use the Gauss's law. And here we find that the normal component of B is continuous at the boundary, and second law, that is from Ampere's circuitry law, we find that the tangential component of H is continuous at the boundary when there is no current, that is surface current density is 0. So these two continuous boundary conditions can be used to determine the refraction at the interface of the two magnetic media. So here we consider a magnetic media having permeability mu1 and mu2, and we consider a magnetic field H1 B1 or H2 B2. Here we consider a continuous boundary condition, that is normal component of B is continuous at the boundary and tangential component of H is continuous at the boundary. So we use these two boundary conditions that are continuous one. From first condition, that is normal component of B is continuous at the boundary, which is B1n equals to B2n. And here the normal component can be written in terms of angle theta 1 and theta 2. So B1n is equals to B1 cos theta 1 and B2n is equals to B2 cos theta 2. Similarly, we can write the tangential component of H in terms of theta 1 and theta 2. So H1t is equals to H1 sin theta 1 and H2t is equals to H2 sin theta 2. And in place of H1 we can write B1 upon mu1 and in place of H2 we can write B2 upon mu2 because we know that B equals to mu H. So from here we take a ratio, that is sin theta 1 upon cos theta 1, that is in terms of tan theta 1. So B1 is cancelled here and B2 on the right side is cancelled. So we get tan theta 1 upon mu1 is equals to tan theta 2 upon mu2. From here we can get a law of refraction for magnetic flux lines at the boundary, and which is tan theta 1 upon tan theta 2 equals to mu1 upon mu2. And this is applicable only when there is no surface current density at the boundary.